Good morning. This is your Stats Sensei, Mr. Spensei, and this is Death Packet Unit 3B Probability Distributions. And this will be video problems 41 to 50. All right, let's get started. So, in a random sample of 50 mathematics majors at a large state university, their mean GPA on a 4-point scale was 3.65. All right, so we have a mean of 3.65. I'm going to go ahead and make a note of that. That's probably important. With the standard deviation of 0.25, which of the following is most likely true about the GPAs, the distribution of GPAs among the math majors at this university? All right, they didn't tell us if this was normal, if this was geometric, or this was binomial. We don't know anything about that. But it says, oh, we have a random sample of 50. Which of the following is most likely true about the distribution of GPAs? Now, this is tricky question. It's asking about the distribution of the GPAs. It's not asking about the distribution of the mean GPAs. If it's the mean GPAs, we could go, hey, n equals 50, that's greater than or equal to 30, normal by CLT, but it's actually asking for the distribution of the population. So we're going to need to explore further to find out what the distribution of the population is. So they tell us that the mean is 3.65. So I'm going to kind of draw this out. And I'm going to act like it's a normal. Now, I really don't know if it is or not. And then I'm going to go 1, 2, 3, and 1, 2, 3, 3.65. And I'm going to add that 0.25 to it, and I get 3.9. And then I go up here and I go, whoa, 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 wait a second. I can't go above 4. So in this case, now I can go this way, and this is 3.4. This is 3.15 and 2.8, if I did that right, which I'm not sure that I did, 2.9. Well, that's way is good, but this way it looks like, hey, you know what? This looks like it's probably skewed. Two, I don't have 3 standard deviations up. I need to have at least 2 plus in both directions. And I don't even have 2. So that's not going to work. So the central limit theorem guarantees that the distribution is approximately normal. The distribution of the means is approximately normal by central limit theorem because n is 30, but we're not talking about the distribution of means. We're talking about the actual population. So that's not what the question was asking. The sample size of 50, well, by central limit theorem, that would be true, but we're not talking about the population. I mean, the question is not about, is the question is about the population, and this is about central limit theorem. Since the maximum possible GPA of 4 would have a z-score of 1.4, the distribution is skewed left. You know what? We didn't calculate the z-score, so since they did that, let's do that. So z equals x minus mu over sigma. Well, they say the highest score is 4, so 4 minus 3.65 divided by 0.25. What's my z-score? 4 minus 3.65 divided by 0.225. Well, that is 1.4. So Z is definitely going to have to be 1.4 for that. So that looks pretty good. That looks like that might be our answer here. Since the GPA of 4 would have a Z-score of 1.4, the distribution is skewed right. No, we already said it looks like it's this. So that's definitely skewed left. So that's not true. And we had chi-squared is first off is skewed to the right. We haven't talked about it. It's not related. The best answer choice for this one is C. Number 42. All of the following statements are true for all discrete random variables except for which one? The possible outcomes must be numerical. Yes. The possible outcomes must be mutually exclusive. Yes, you can roll on a dice, you can roll a 1, a 2, a 3, a 4, a 5, or a 6. But on a single roll, I can't roll multiple, so that's true as well. The mean expected value always equals the sum of the products obtained by multiplying each value by its corresponding. Well, that's true too. The standard deviation of the random variables can be never be negative. Standard deviation can never be negative, so that's true. Then finally, approximately 95% of the outcomes will be within 2 standard deviations of the mean. That is only true for the normal. That's only true for the normal. We can have all sorts of distributions that are not normal. The dice is uniform. It doesn't have 95% between plus or minus 2. If it's skewed right or skewed left, it's not true. That's only true for the normals. This is my answer because this is a false statement. Philippe recorded 75 observations on a certain variable and then calculated the mean and the standard deviation S for the observations to help decide whether a normal model is appropriate. He created the following chart. In Philippe's charts, the letters A, B, and C, D, and E represent the number of observations falling in each interval. Okay, so if this was a normal, plus or minus 1, 68%. That's where the bulk of the information is. All right, out here, we don't have a whole lot. All right, not very much out there. So, which of the following counts for AB is the best indicator that the variable can be modeled by a normal? Well, if it's a normal, I'm going to have a hump in the middle and very little in the edges. Well, when I look at this one, it goes, well, we start off low, go high, then we come back down. And this one looks like it's bimodal. That's not normal because normal is going to look like that mound shape. This one, well, this one is mound shaped, so I like that because it goes from 2 to 10 to 51 to 10 to 2. So let's see if we can use that, and hopefully that's going to be our answer because that one looks good, but let's see if everything else looks bad. Well, this one, part C, so this is B and this is A. This one's looking good. This one's not. C, we're starting at 3 and we're going up and up and up, and it's like, oh, that's not it. D, on the other hand, is started high and going down. So that's not it. And E is a uniform model. So that's not it because I needed it to be mound shaped to be a normal. So it's not E. My best answer choice is B for 43. Moving on to problem 44. All right, the waiting time for a commuter bus is normally distributed with a mean of 8 minutes. All right, so we have a mean of 8 and a standard deviation of 2. If there are 3,000 riders a day, which of the following is the shortest interval with 2,000 riders? Okay, shortest interval. All right. Shortest interval is always going to be centered about the mean, and they told us this was normally distributed. Well, that's true if it's normally distributed. In this case, it's normally distributed. We have a mean of 8. And we're going to go, okay, 1, 2, 3. So this is 10, this is 12, this is 14, this is 6, this is 4, this is 2. And we had 3,000 riders. What interval has 2,000? Well, 2,000 divided by 3,000 is 0.667. All right. Well, one thing I know is plus or minus 1 standard deviations has 68%. So it's like, oh, the shortest interval is always going to be centered on the mean, and I need 67% or 66.7, and this is 68. So I need to be looking for something that's close to 6 and 10. Well, 0 to 9, no. 6.1 to 7.1, no, that started about right, but it didn't even go up to the center. 6 to 8, no, that's about 34%. Oh, this one's pretty close, 6 to 10. So I'm thinking this is probably my best answer. Let's check it out. Let's go use a normal CDF. Second vars, normal, CDF, my lower, 6.1, my upper, 9.9, my mean, 8, my standard deviation is 2, and I get 0.65788. That's the probability. Let's multiply that by 3,000. Should be close to 2,000. 1973, not too far off. Anyway, by empirical rule, that is my best answer. Okay? So this was a testing on the empirical rule. So which of the following statements are true statements? The area under the normal curve is always 1. Well, that's true for all probability distributions. So regardless, that's always the case for all probability distributions. So that's true. The smaller the standard deviation of a normal curve, the higher the normal the graph. All that's saying is if I have a small standard deviation, it's going to look something really tall. If I have a big standard deviation, it's going to be shorter and fatter. All right. And that's a true statement. Normal curves with different means are centered about different numbers. Yes, you'll be centered about 0, 10, 100, anything. You can be centered about whatever the population mean is. So that's also a true statement. So which are true? 1, 2, and 3 are all true. Number 46, the mean and standard deviation of the sample data collected on a continuous variable y are negative 0.5 and 0.5 respectively. So my mean is negative 0.5 and my standard deviation is 0.5. By the way, standard deviations can never be negative. The following table shows the relative frequency of the data given. All right. So let's go ahead and based on the table, is it appropriate to use the normal to approximate this? I don't know. Let's find out. Well, if it were normal, it would have to look like this. And let's go ahead and draw this. So this would be my mean, and I'll go ahead and put negative 0.5. 1, 2, 3. Negative 1, negative 2, negative 3. So this is going to be 0 because we're changing by 0.5. This is going to be 0.5, and this is going to be 1. This is going to be negative 1, negative 1.5, and negative 2. All right. It says that I'd have 25% of my data. This says 25% right here. It's like, no, 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 no. We don't have that much between there. Between negative 1 and 0, or from here, I should have 68% of my data. Or from here to here, I should have 34%. These don't come anywhere near matching. So no, and it's no, not because 0 is not the center. 0 doesn't have to be the center. All right. No, because the distribution does not indicate a bell shape. Yeah, it doesn't. These, when I look at this, oh, this is 25, 15, 10, 10, 15, 20. This is what it actually looks like. It looks something like that, which is not bell shaped. So my best answer choice to 46 is D. All right. Number 47, the waiting times for a new roller coaster ride are normally distributed, okay, with a mean of 35 and a standard deviation of 10. If there are 150,000 riders in the first summer, which of the following is the shortest time interval with 100,000? Well, please remember, if it's a normal curve, we have more area in the center. Consequently, the shortest interval will always be centered about the mean. So 35, 45, 55, 65, 25, 15, and 5. We have 100,000 out of 150. So 100. Let's take the calculator and we'll divide that out. Oops, too many commas. And when we do that, we're going to get about 2/3. 100 divided by 150, and we get about 2/3, or 0.666. Well, that means Hey, we want 68%, about 68%. Well, 68% is plus or minus 1, and we know we have to be centered on the mean if we want the smallest interval. So what one is the smallest interval centered about the mean? And about 25 to 45 is what we're looking for. So C, 47 should be C. All right, and we can just use the empirical rule to estimate that. Next one, the waiting time for a commuter bus is normally distributed with a mean of 8 and a standard deviation of 2. I believe we already did this one. So sorry for that appearing twice. So 8, 10, 12, 14, 6, 4, 2. And because they told me it was normal, and we had a mean equal to 8 and the standard deviation equal to 2. So I just add my standard deviations across. And we have 2,000 over 3,000, and that equals 0.666. And I know by empirical rule, and again, this is testing your empirical rule, that between plus or minus is 68%. And they want the shortest interval. If you want the shortest interval for a normal, you will always be centered about the mean. So the shortest interval for a normal is centered about the mean. So we're going to be looking for something that has close to 6 and close to 10, and D is by far our best. All right, number 49. A piece of clothing takes an average of 38 minutes to move through an assembly line. Okay, so tell me my mean is 38. If the standard deviation is 4 and the distribution is normal, what is the probability a piece will take over 45? So we're looking for the probability that X is greater than 45. And I really don't need that. So let's draw a picture of that. Here's my mean of 38. 45 is up here. And we have a couple different ways to go about this. All right, so here we go. Stat, test, z-test, and I can do it this way, and where I have a mean of 38, the standard deviation of 4. I'm interested in a value of 45. Only am worried about a single piece, or 1, and we want it shaded to the right. And when I do that, I get a calculated value of 0.0400. That's one way. The other way is to go second vars, normal CDF, and we have we have a lower bound of 45, an upper bound of 9 raised to the 99th power, a mean of 38, a standard deviation of 4. And we still get the same thing, 0.0400. So two different ways to approach that. And you really do need to know both. All right, number 50. The average noise level in a bar is 36 decibels. So they're telling us the mean is 36. What is with a standard deviation of 5? Assuming a normal distribution, what is the probability the noise level is between 30 and 40 decibels? All right, so if I'm drawing a picture of this, my mean is 36, and I have a 30 here, and I have a 40 here. I'm looking for this area, so I want the probability that 30 is less than X is less than 40. Now, there's two ways to go about this. I'm going to show you the long way first because it's also important you know this. So we're going to go to stat, test, z-test. My mean was 36. My standard deviation was 5. Oops, not 4, but 5. And we have a lower of 30, so we're going to calculate that first. And notice that it's shaded that I have it that way, so press enter. And I end up with a 0.1150. And then I'm going to need to do the 40. stat test, z-test, doing the same thing, just changing it to a 40. And I'm going to get some larger value of 0.7881. I subtract those. 0.7881 minus 0.1150. Now, it's real important you know this method, but the fast method for this problem is just to go second vars. Oops. Second vars. Normal. CDF. Lower bound. 30. Upper bound. 40. Mean. 36. Standard deviation. 5. And we can do it all in one place, and we get exactly the same answer. The thing is, ultimately, someday we're going to have to give those z-scores. But since this is multiple choice, norm CDF would have been the fastest. All right, next problem. Oh, that takes care of this video. Appreciate you watching, and I sure hope to see you on the next one. Thank you.